All right, our second speaker is Yifan Hong from Colorado. He's going to be telling us about quantum memory at non-zero temperature in thermodynamically trivial QLDPC codes.
Okay, I guess this works. So yeah, thank you. Thank you for coming to my talk. And I guess hopefully the goal, so the end of the talk, maybe this title hopefully will make more sense. And okay, so sort of the structure of this talk, I'll give some motivation into the problem, and I'll introduce sort of what the problem of self-correction is. Then I'll give our main results for LDPC codes. Then I'll sort of briefly glance over some practical implementations and sort of applications of our results, and then end with some summary and open questions. Yeah, so I guess similar to what Chow said in the previous talk, this maybe is like coming from the physics perspective to talk about error correction. And so first, I'll just give like a short primer on what does self-correction mean, or what does it mean for code to be at non-zero temperature. Typically, the situation is that we have some system defined by some Hamiltonian, which maybe in some subsystem we have some information we want to protect, say in its ground states, and then we attach this Hamiltonian into an environment, maybe at some non-zero temperature T, and we allow it to exchange energy. And in physics, this would be typically called the canonical ensemble. And up to some very broad, up to some broad assumptions and minor some special exceptions. After a long time, we essentially expect the system to reach its thermal Gibbs state, which is, you can think about it as the state that maximizes entropy with respect to some constraints like average energy. And so the key word is, this word long can typically actually mean a very long time, right? And because typically thermodynamics is about some steady state quantity, which you wait infinitely long. When I have a finite size system, right, you might have to wait a very, very long time in which, on our time scale, we may not observe actual thermalization. And so sometimes this can happen, for example, if I have this energy landscape here, sort of the bottom right diagram, and if I start in one well, thermalization will tell me, well, because the other well is at the same energy, I should spend equal time eventually in both wells, but it might take actually a very long time for the system to sort of tunnel through to the other well on finite time scales. And normally when this happens, right, our system will retain some memory of its initial condition, and we say it sort of fails to thermalize or fails to mix. And we can leverage this fact to protect information inside. Okay. And so more concretely, how do we model this system-bath interaction? We're going to use a discrete time Markov chain. And so the Hamiltonian is the typical Hamiltonian you get. For example, if I have a code, it's just going to be, if I have a stabilizer code, it's just going to be the sum or the minus sum of all the parity checks. What we want for this Markov chain to have is what's called detail balance. And microscopically, this is sort of reflecting some time reversal symmetry in the dynamics. But sort of more mathematically, we want this because this ensures that the Gibbs state or the Gibbs distribution is going to be the unique stationary distribution of this Markov chain. Okay, we need this and then also the condition of ergodicity. And so sort of this diagram on the bottom right shows, like, for example, this bold X could be like different states, separated by different energies. And we can have jumps between the different energies. And the probabilities of these jumps will be given by this Gibbs factor, which is like e to the minus energy difference over temperature. One thing we also would require is that the system-bath interactions are local. So the bath only interacts with a constant degrees of freedom at a time. And this is typically a very physically motivated assumption. And so some examples, you can take your typical off-the-shelf Markov chain Monte Carlo algorithms like Metropolis, heat bath, or Glauber dynamics, which are, they have different microscopic rules, but they all satisfy this overall detailed balance equation. And so they all converge to the same distribution at the end. And so for a classical system, so like for classical bits, these would just be spin flips. But for a stabilizer model, these would be local poly jumps. And this is unique because for a stabilizer code, you can actually, you can jump between all the energy eigenstates with just poly operators. And so like more or less like, the Hamiltonian for stabilizer code, at least when you do this Gibbs sampling, is more or less the same, morally the same as just classical Gibbs sampling. Okay, so what do we mean by self-correction memory time? Well, the problem is precisely stated as we first encode. So we have some code which defines some Hamiltonian, right? The code will encode some information in it, then, and it will be in the ground states of this Hamiltonian. Then we will allow the system to interact with the thermal environment for some time t. And then we ask, okay, if we remove the system from this thermal environment, is the information still preserved? And so we do this final decoding map because there will be some final errors. And so we essentially ask, well, are the final errors going to be small enough so that we can actually recover our initial information? And so, yeah, when use these local sort of Markov chain rules, you can actually imagine as some sort of like noisy local error correction. For example, well, here I've done the microscopic rules for globber dynamics, and you can imagine as actually you're doing some local bit flip decoder with a failure rate. So I just ask, okay, I pick a bit at random, and I say, well, if I flip it, will it lower the energy? And if it does, then you always flip it. But maybe you fail with some small probability, which is going to be related to the temperature by this rule. And so yeah, typically the self-correcting memory coherence time is the time in which the successful decoding probability at the end is going to be order 1. And typically when we say a code is self-correcting, we say there's some critical threshold probability or threshold temperature below which this memory time will diverge exponentially with a function of the system size. And sort of as a concrete example for the usual like paradigmatic example of self-correcting memory for the 4D toric or surface code, this coherence time diverges in the polynomials n to the 1/4. Okay. So now that I've sort of given the premise of this, I'll say our main results, but first let me just give a sort of another primer on LDPC codes. So these codes are typically constructed from expander graphs. And if you're not familiar with expander graphs, all you need to know is that they have this boundary proportional to volume ratio. And when you zoom in on like a certain neighborhood of this expander graph, you'll see what looks like a locally tree-like graph. And it turns out when you build codes using expander graphs, because of this boundary volume proportionality, what you can get is that the number of violated checks or the energy for a given error string will actually be linearly proportional to the size of the error. And typically, and I guess in the literature, people would call this confinement. And it's linear because it's a linear proportionality. And it's up to some cutoff, which I've called capital gamma. And so there's a linear confinement, this simple plot on the bottom right, basically just saying, okay, you have the slope, the slope's alpha up to some cutoff gamma. And right, the actual energy barrier might be higher, but this is just a lower bound. And so for expander hypergraph product codes, so hypergraph products of classical expander codes, it's known that in certain families of these codes, this energy barrier will be around like square root n. And then for the good quantum LDPC codes, these will scale linearly. Right? And I guess historically, right, these were sort of used to actually prove that the distances are linear in n. Okay, so our main result is that this linear confinement property actually gives us the self-correction property that we want that I've defined in the previous slides. And so, for example, if I use the hypergraph product code, right, it has this linear confinement up to square root n. There exists some constant critical temperature, and below this critical temperature, this self-correction memory time, which was based on this flowchart from the previous slides, will diverge exponentially in the energy barrier square root n. Yeah, and so the proof strategy we'll use, right, because we've modeled the system-bath interactions as a Markov chain, will show that in order for a logical error to happen, the system must pass through a very improbable bottleneck in the configuration space. Okay, so sort of as a warm-up, we'll do the case with a linear energy barrier, and then I'll talk about sublinear first. So the simplest scenario I would say is when the energy barrier is linear. So this capital gamma is proportional to n with some proportionality constant small gamma. And yeah, right. And this immediately implies the distance will also be at least this energy barrier. So we'll define the bottleneck to be at half the energy barrier. Well, half is for technical reasons, but right, it's around the energy barrier. And notice that because, oh yeah, and then this, so this diagram's in Hamming space. So notice that because, right, our bath acts locally on the system, in order to go from, say, x0, our initial code word, to another code word, either x1 or x2, right, locally, it has to pass through this. It has to pass through this bottleneck. And so we can do a simple bound, right? So the probability that of x0 going to this bottleneck set at the energy barrier, first, right, we use detailed balance of the Markov chain to show that, okay, this is going to be a sum of all the states in the bottleneck, and then with the Gibbs factor, the energy penalty. So that's basically just a simple union bound. And then, right, and then we can bound this, upper bound this Gibbs factor with the linear confinement that these codes have. And so this right side, right, this is like the Gibbs factor of coming from confinement. And this is a simple sum over how many states are in this energy barrier. It's an upper bound. Right, and then we can simply just upper bound this entropy contribution with 2 to the n, right? And then notice that in this expression, right, we have two exponentials. Both in the exponent, they're linear in n, which means when beta, the inverse temperature is large enough, this whole thing will be exponentially decaying in n. And indeed, that is the case, right? So then when we invert the expression to find the expected time, right, then we get something that's exponentially growing in n. And so, yeah, this factor of 1/2 was just so the time to reach, let's say, like almost distance over 2 errors is going to be exponentially long. And so, right, and so with high probability, before this time, if I remove my code from the bath and I decode it, I will decode it with high probability successfully. So for, I'll just let this sit for like, okay. So what do you do for sublinear distance? Well, or sort of sublinear energy barrier, then we sort of can't use that simple proof before, because now our Gibbs factor is not scaling with n. It scales sublinearly with n, so we can't do that argument, but we haven't leveraged the sparsity of the graph yet, basically the fact that our code is LDPC. And we can use this to show that, well, actually, even if you have a sublinear energy barrier, right, typical error configurations, they usually won't conspire to form these long error strings that are detrimental to the code. And it's almost the same, sort of percolation argument people use to prove thresholds for stochastic errors. Right, and because, right, the code is LDPC, you can imagine every qubit only interacts with some, constant number of other qubits through the parity checks. And so, right, so you can bound essentially the probability that what are the odds that the environment forms this big connected cluster of size S. And let me just go through what this formula means. So first, you pick any qubit, so there's n of them, so there's n. And then, right, from the starting qubit to get the second qubit, there's z neighbors, so you can pick any one of those, and then there's z neighbors for the third one and the fourth, so then you have z to the s for a cluster of size S, and then you have this linear confinement energy penalty. And notice now that, right, we have, in the exponent, we have s on equal footing, both z to the s and this Gibbs factor here. Right. And then, right, essentially we just set s to be the confinement barrier, and then immediately, right, we get something that's, for low enough temperatures, we get something that's exponentially decaying in s, and then we just invert that to get a bound on the memory time. Okay. Yeah. So let me just briefly say something like about the thermodynamics of these codes. And so from the physics point, this is actually kind of surprising, because if I write out the partition function for the code, and so this will be a statement about the actual steady state of the system. So yeah, and so the quantity of interest will be this partition function. And then because I have a CSS code, it just factorizes into essentially like an x and a z component. Okay, this H is the parity check matrix, so it's different than the Hamiltonian, but it's related. Right, we have an error syndrome equation. The parity check matrix essentially maps us between physical errors and error syndromes. And in the hypergraph product code, typically the x and z parity check matrices will have full rank. And so every row is like an independent constraint. And what that means is actually that every syndrome has the same number of possible solutions for errors. So every syndrome is valid. And they all differ by code words, and there's 2 to the k different code words. And so they all have the same degeneracy. And what this means is you can actually, the partition function, you can, it actually factorizes. You can essentially evaluate it exactly in the syndrome basis. So the basis of fixed stabilizer eigenvalues, you can think about it that way. And you get this smooth function as a function of temperature. And so thermodynamically, at least physically, right? So there's no thermodynamic singularity in the partition function, and so usually we can't. And so typically you would say there's no phase transition in this model, at least from the static thermodynamic perspective. And so this is sort of the surprising thing because, right, previously I showed you have the self-correction phenomenon, and in models like the 40 toric code, actually the dynamic phenomenon is self-correction, and the static phenomenon of the equilibrium distribution actually coincide. But for these sort of expander graph codes, it's sort of the most extreme where actually on one side it says there's no thermodynamic phase transition, but sort of from the dynamical perspective, we still see the slowing down of the dynamics. And sort of as a secondary result, we extend this to codes where you actually have sub-extensive rank deficiency, not just 0 rank deficiency in the parity check matrices, using what's called a Cramer's 1A argument. OK. So with my last few minutes, I'll just sort of glance over some practical implementations. And so actually, what's sort of, to me, the most exciting part about this is it enables you to do what's called measurement-free quantum error correction on these codes. And roughly what measurement-free quantum error correction is, let me just describe it in this example circuit, right? You have your physical qubits, say Q1 to Q5. You have your ancillas, which are going to measure your stabilizer checks. You have the syndrome extraction part. And then typically after you do syndrome extraction, you would measure the ancillas and do some classical feedback. But here actually, right, the ancillas already hold the syndrome information, so you actually just run the decoding algorithm at the quantum level. And then you can just trace out the ancillas. And so notice here we've not done any like projective measurements and feedback. And so one way you can think about it is actually that errors from the system are removed when you trace out the ancillas. So you're almost like removing entropy from the system through like the quantum circuit, and then when you trace it out, that's how noise is removed. Yeah, mathematically, this is related to ordinary like measurement-based error correction with a Stein spring picture, because you can always say a measurement is just some isometry in a larger Hilbert space. And so from an experimental perspective, this may be nice because in neutral atom platforms, typically it's very long. It takes a very long time to do projective measurements, and it's much faster to just do like a destructive measurement or a reset. All right, so here's the procedure to do this measurement-free quantum error correction using this like thermal decoder that I described earlier. And so this was, we're going to follow the procedure in the topological quantum memory paper in 2001. Essentially, you could, like, for simplicity, select a data qubit at random, look at what checks it's connected to, perform your single ancilla syndrome extraction. But crucially, at this step, you don't measure the ancillas yet. And then you just perform a simple reversible Boolean circuit, like majority vote, on the ancillas, and then control unitary, apply back to the data qubit as the recovery operation. And then once you're done, you trace out the ancillas and repeat for other qubits. And note that you can parallelize this to all qubits because the code is LDPC. And just remember that, from I guess the first few slides, when you have noise in this decoder itself, you can view it as essentially raising the temperature, And because there's a threshold, this procedure can tolerate a certain amount of noise and still be fault tolerant. And something I just want to emphasize as well is that this, this simple majority vote sort of thermal decoder has a much lower complexity than other local decoders for hypergraph product codes, such as the small set flip decoder, which, because it's local, you can sort of also do this way, It's just that the step 3, when you do this, when you actually do the quantum circuit decoding, it may be more complicated, And so overall, like the way error correction is going to look like is essentially you run finite depth circuit, trace out qubits, finite depth circuit, trace out qubits, and then this actually will preserve your information, and there's no measurements. All right. Yeah, so sort of connecting this to earlier literature, right? Sort of originally, I think confinement is used to prove like linear distance bounds for classical codes and linear distance bounds for quantum LDPC codes. And then sort of more recently, it was shown that this like linear confinement property is actually sufficient to give you single-shot error correction against stochastic errors. And then sort of our work shows that it's also a sufficient condition for self-correction in LDPC codes. Okay. And sort of in the broad scheme of things for like different quantum memories, this is sort of where our results will fit into this like large, like this encyclopedia of codes, sort of. And the orange question marks are things I wasn't entirely confident on, so I didn't want to like say something wrong. All right. Yeah, and then so some open questions, I guess, related to both the previous talk and this talk. So first, right, I've talked about the actual, like actually preserve information, but it depended on actually encoding the state first. So there's the whole problem of like, how do you encode the state fault tolerantly, and can you do it sort of without measurements as well? And that's actually an open question for hypergraph product codes, but it was recently solved for the 2D surface code. Right, and then from the more physics perspective, like what if we add perturbations to the Hamiltonian? And then this would be sort of like combining, the results of the previous talk and this talk together. There's some progress that's made, and the solution's it's been solved for the good codes where the energy barrier scales linearly. It's not obvious actually how you would do this at first, right? Because once your Hamiltonian terms don't commute, it's not clear, like the eigenstates could delocalize. It's not actually clear like what the eigenstates actually look like or how you actually even do local jump operators. And sort of on the more complexity theory side, right, there's the problem of like actually, okay, preparing the Gibbs state, and because of these recent NLTS results, it sort of implies, okay, maybe there's a class of Gibbs states where actually like you can get this circuit complexity transition from like, being able to prepare it in finite depth to non-finite depth, but maybe it's somehow also invisible to thermodynamics, sort of like how self-correction was. And this would just be kind of surprising. And yeah, let me just end with acknowledging my collaborators, and yeah, thanks for your attention.
Good talk. So I have a question about this trivial thermodynamics statement. So what goes in there? Because I know two counterexamples on two sides of LDPC codes. One, I think, is just regular surface code, which gives square lattice Ising model, not trivial. And the other is the other extreme limit. So if you look at any finite rate quantum LDPC code with a power law distance, that has non-trivial phase because logical operators have rank, reduce the rank of check matrices so that you are really a finite fraction of the rank is occupied, and so you can prove that duality has finite density of defects. So free energy duality is, there are inequalities that you can prove. And so question is, what goes into that statement about trivial thermodynamics?
Yeah, so the statement I made about trivial thermodynamics was solely based on the fact that the partition function is smooth. And so typically, like, thermodynamic quantities like free energy and heat capacity that you would derive, that typically you would use for signatures of phase transitions, right, just would not show them. But sort of what you asked about, like free energy of defects, yeah, I mean, if
I'll show you the reference where it is proven.
Okay, yeah, I'd be interested in seeing that. Yeah.
Thank you for the very nice talk. So if I heard you correctly, you made a distinction between measurement and tracing out the ancilla. But if I understand correctly, tracing out the ancilla also need to measure and then reset. So what's the difference in practice?
Yeah, I guess in practice, I would say it's the difference between you want to do like a non-destructive measurement, which in some systems is slow to do, I believe, versus doing a destructive measurement where, like, for example, your qubit might be kicked out of the computational basis, right? Right. Typically, for non-destructive measurement, you want to measure the qubit and have it stay like, if you measure 0, you want it to like stay in 0 so you can measure it again. Versus maybe like for a destructive measurement, if you measure it, right, you get like 1 photon, but then it like disappears out of the computational manifold, and so you sort of can't do it again.
And from this perspective, why tracing out is better?
Well, I guess I would just say it's like, maybe doing the destructive reset is just easier because you don't have to like read out what the actual outcome is, right? Okay, yeah.
Yeah, thank you for the nice talk. I really liked that this lack of phase transition leads to the possibility of measurement-free QEC. So is this like a proven necessary sufficient condition? And also, could you comment on the fault tolerance aspect of it?
Oh, once you prove there's a self-correction threshold, then immediately you can essentially run, right? You just like simulate the heat bath dynamics with this, like this procedure, right? Like in this paper.
So it's like a proven necessary condition.
I guess I would say the self-correction is sufficient for this decoder. You can prove that this decoder will work. Yeah.
In the fault tolerance setting.
Yeah, yeah.
I sort of had a related question. So at the end, you showed the application is actually doing coherent error correction. Could you replace that with just measuring the ancilla and then projecting back to the code space?
Yeah. So technically, for step 3, right, you could you could just measure and then like feed it to a classical computation, right?
Yeah. It'd be cheaper than applying a whole bunch of control NOT gates.
Yeah, you can do you can use this decoder and do like traditional measurement-based error correction.
Thank you for the nice talk. So 2 quick questions. So you mentioned that the error model that you're considering is a local interaction with the bath. So in practice, you might have some, correlated errors which break this assumption to some extent. So can you make some statement for those kind of errors? And the second question, so if I'm not mistaken, so you're proposing a new kind of like decoding approach, right? And like this approach of tracing out like ancillas, etc. Is it something that you have also like numerically studied this and made comparison with other decoding approaches?
Yeah, I guess for the second question, I would say I haven't numerically like looked at a specific code family and like found like what the circuit level threshold for this procedure is. But for your first question, if by correlated errors you mean like if I do a circuit level model and I have error correlations because I've run like a finite depth circuit, then I would say like sort of because it's a finite this procedure is a finite depth circuit. At most, the correlated errors can only affect some like light cone finite light cone amount of qubits. And so sort of I can in the proof, it just means maybe in my like when I choose my bottleneck set, I just have to like thicken it a little bit more. So there's some like order 1 constants that would change, but otherwise the overall qualitative behavior would be the same.
Thank you.
Sorry, we're out of time. But maybe any further questions can be taken offline. So can we thank the speaker again?